start talking. Hello, this is Yuta Horii from, last year I was in the undergraduate in the University of Tokyo. And actually, I'm right now in Tokyo, in Japan, and it's 10 o'clock p.m., so it's very dark around me. Okay, I'll talk about my presentation. Physical reservoir for computing in a soft swimming robot. And this is about the abstract of what I'm going to talk today. So I'll get on into the inside. First, this is the robot we made, and this is showing my desktop, but the swimming robot is moved completely by closed loop control. So I will talk about my background. So as for conventional control schemes for swimming robots, many swimming robots have been developed to realize swimming capabilities similar to real robots, real fish, using engineering approaches. So many of these robots have adopted methods such as controlling multiple actuators using physical models like this, or introducing hierarchical architectures and switch behavior top-down based on sensor information. However, these methods are not quite as the same as for fish. Bill et al. Showed that fish might solve difficult problems in underwater environments by using their body. This video shows that this is not a live fish, it is the body of a dead fish. And they can passively produce swimming motion in vortex wakes. So focusing on this idea of embodiment, other studies have achieved swimming with high efficiency and high maneuverability by adopting soft materials and mimicking the physical properties of fish. Like in the picture in the bottom right, Saluma and Katsuma achieved propulsion by waving a fish-like rubber fin. And other studies have achieved three-dimensional locomotion with only one motor by using soft materials. However, these researches still have room for improvement in terms of high environmental adaptability and complex decision-making ability that fish possess naturally. So this is what we have focused on. Get to the next slide. So we focused on physical reservoir computing. This is a machine learning framework that uses physical dynamics as a computational resource. In the field of PRC, the dynamics of physical components, such as octopus arms made of silicon or flexible spines of quadruped robots, such things were used as a computational research resource. Reservoir computing, which is the premise of PRC, is a framework for recurrent neural network. It's shown here. Training that consists of an input layer, an intermediate layer called the reservoir, and an output layer. Reservoir computing is characterized such that training can be performed by updating only the readout weights right here, while the weights inside the reservoir are usually fixed during training. And many components can be a good reservoir if it can possess these properties: separation property, approximation property, echo state property. And separation property and approximation properties are common functions in RNN, requiring the system to distinguish different inputs and map them correctly. Echo state property requires the output of the reservoir to depend only on the previous input sequence and not on its initial state. So these properties are important. However, these conditions do not guarantee that the system works sufficiently for the desired task. So our aim is to show that the swimming system, including the dynamics in water and body, meets the specified conditions and can be used as a computational research in motion emulation, as well as in environmental state estimation. So what we done in this study is that we made a soft street-like swimming robot, and we made the robot to learn swimming motions through open loop supervised learning using the PRC framework. And we made the robot to produce swimming motions through closed loop control and made it to estimate environmental states through open loop control. So this is a robot design. We used only one servo motor to produce swaying motion. And here, this is a characteristic part of this robot. We used a soft silicon rubber sheet, and eight bend sensors are embedded in the rubber sheet to take so that it can detect the shape of the rubber sheet. And the sensor outputs were amplified by Wheatstone bridge circuits. So this is a learning rule and feedback control of our robot. This equation shows reservoir dynamics. R is the reservoir state, and Y is the target motor command, and Q is the environmental state. So the reservoir state is defined by the target motor, the previous reservoir state, and the environmental state. And X is the observation of the reservoir state, which is in our experiments is sensor outputs. And the readout function is merely a linear regression. So we use linear regression for learning. And the target motor command in this experiment was a sinusoid motion. So we'll get into experiments. We have done mainly 2 experiments in this study. The first one is the experiment on emulating swimming motion in a fixed environment. The purpose is to investigate whether our system satisfies the necessary conditions for emulating swimming motions, and to investigate whether there are differences in performance depending on the motion to be learned. So this is a procedure. It's a simple procedure. We obtain the applied motor through open loop control, and we learn the weights by linear regression, and we drive the robots with closed loop control. And the variable parameters were the wavelength and amplitude of the target motion. So these are the results. We changed the wavelength and amplitude, and so many times in the left, where the wavelength is very short and the amplitude is large, the robot created this periodical motion. However, on the right, where the wavelength is longer and the amplitude is smaller, it did not create a sinusoidal motion. It looks like a very distorted motion. So this shows the results for other amplitudes and wavelengths. This grayed out part was where the robot couldn't produce any motion or created a very distorted motion. And so the left upper part, where the air amplitude is very large and the wavelength is very small, this dynamic part, the error was very small, but other parts, there were failures. And the error in wavelength, the left figure, was very small. So it shows that the system can emulate a certain temporal task. However, emulation fails at these grayed out conditions where amplitudes were small and wavelengths are large. The target motion in these zones might not have been dynamic enough, and the system did not have sufficient input separability to perform the task. And please look at this red part where the condition of amplitude in wavelength is 830. The error was large, and the system generates a motion with a larger amplitude than the learning motion. And this might show that the nonlinearity of the system is maintained by generating an exaggerated motion. And here we put manual perturbation to the produced motion. You can see that the robot shows a high robustness to external perturbation. And the effective perturbation is mitigated over time. And it shows that the system has a state forgetting property. The second experiment was environmental state estimation. The purpose is to investigate whether the robot can discriminate the state of the environment through its motion. So the method, it's difficult to see, but there is a string put on the head of the robot, and this string was pulled up and down, and we tried to see if the robot can detect these differences through the same motion. So the procedure is like this. For both states up and down, training was done, and linear regression was done for the combined data sets from up and down. And by using these, and the learning method we used is logistic regression, which is mainly used many times for detecting 0 and 1. So this is the result. For a condition where the wavelength was 640 and the amplitude was 40, the estimation accuracy was 0.991, but for 850, the estimation accuracy was 0.529. And however, you can see that the shape of the sensor outputs are different enough. However, for condition 2, the estimation accuracy was extremely low. So the discussion is that can we achieve the higher accuracy by changing the readout part? In the previous experiments, we estimated the environmental states using sensor outputs from only one time step. So we used, so we thought that if we can use more time steps, the estimation accuracy would be better. So as for the left one, it reached 100% accuracy, and for the condition 2, the accuracy reached to about 0.85 by using about 100 time steps. So this shows that by changing the readout part, the estimation accuracies can get better. So our conclusion, we succeeded in emulating swimming motion. We could distinguish two different environmental states by altering the readout part. And these results indicate that the swimming system satisfies the properties needed for PRC. So our future aim is to achieve more complex and non-periodical motions and achieve swimming optimization and achieve motion switching, which fish can actually do. And at last, we think that we can apply this architecture to other soft swimming robots. Thank you for listening.
Thank you very much, Yuta. Very interesting. And thanks for the nice presentation. We have some time for questions, so please don't be shy. And so I can start with one. I was wondering, so did you think of extending your work to like optimizing for the motion, let's say for energy efficiency or for certain quantities that you would like to optimize?
Yes. Oh, Excuse me. So
yeah, I
so
think
your question
you
was
have it
that.
somehow here on this
Yes,
on this slide with the
yes.
reinforcement learning. Did you already try this out a bit? Do you have some ideas? Would that work or?
Actually, I haven't tried it yet, but other past researchers have shown that it was not actually a physical reservoir computing, but by using the reservoir computing, actually reinforcement learning was done. So by taking the speed of this robot and using that as a goal, I think we can achieve this. Well, if this reservoir is this physical reservoir is can be used as a normal reservoir that was like shown in those past researches.
Cool. So do we have questions? Not yet. Please put your questions in the Q&A panel or here